into compound probability and tree diagrams. In order to work with compound probability, we're going to have to make sure that we're comfortable multiplying and adding fractions. So, just a little bit of a review of multiplying fractions. If we want to multiply 2/7 times 3/5, multiplying fractions is really a pretty straightforward process. All we need to do is multiply numerators. 2 times 3 is 6. Multiply denominators. 7 times 5 is 35. And 6/35 might be able to be reduced, but since we're talking about probabilities in this section, you don't have to worry about reducing. Just make sure when you're multiplying fractions with multiply numerators, multiply denominators. Adding fractions. That's going to be more important for us on Thursday when we get into section 4.5 actually. But since we're doing this little review, I think we can do both of those at the same time. If we want to add 2/7 plus 3/5, we can't add those the way they're written. And it's because in order to add fractions, you have to have a common denominator. We can multiply fractions that don't have the same denominator. That's no problem. But to add them, they have to have the same denominator. So we have to think of a number that 7 will go into, that 5 will also go into. And if you can't think of one, that's all right. You can just multiply those two numbers together to get one. So if we do 7 times 5, we can say, okay, 35 is a number that 7 will go into. 35 is also a number that 5 will go into. So I will use 35 as my common denominator. Now, I can't just write that as 2/35 and 3/35. If I change the denominator, I have to change the numerator because I want my new fraction to be equivalent to my old one. What I mean by that is, if we have multiplied the denominator by 5, then we also have to multiply the numerator by 5. And so what we end up with here, 2 times 5 would be 10. What we're saying here is 10/35 has the same value as 2/7. Those two fractions are equivalent to one another. It's just for this particular problem, I need 35 as my denominator, so I'm going to rewrite 2/7 as 10/35 because then I'll be able to add it to this other fraction that I'm still working on. When I look at the fraction on the right, okay, well, let's see here. I have to multiply 5 by 7 to get 35 in the denominator. If I multiply the denominator by 7, I also multiply the numerator by 7. And when I do 3 times 7 there, what I end up with is 21/35. What we're saying is 21/35 and 3/5 have the same value as each other. Those are equivalent fractions. It's just because I'm trying to add these together, what I need to do here is make sure that they have the same denominator. Now they do. I have 10/35 plus 21/35. A way to think of that is I have 10 of these plus 21 of these. And when I add those together, I add the numerators. 10 plus 21 is 31. The denominator just stays the same, 35. So I wind up with an answer here of 31/35. And again, I really like thinking of it this way. I have 10 of these plus 21 of these. So in the end, I have 31 of these. 31/35 is what we end up with. Multiplying fractions, our process is multiply numerators, multiply denominators. Very simple, very straightforward. Adding fractions, which will be more important for us on Thursday when we do expected value. But it's a nice place to do the review because we can contrast those two operations. When we add fractions, we first have to make sure that we have a common denominator. If we don't have a common denominator, then we need to change our fractions. We need to create equivalent fractions to the originals, but now they have the same denominator, so we can add them. When we add them, We add the numerators together, and denominator just stays the same. Any questions about that little review we did before we get to our probabilities that we're going to talk about today? Outstanding. Based on the way that you all perform, my guess is you're pretty comfortable with everything we talked about there on that last page, but I do think it will be valuable for some students. Compound probability. What that's about is events that happen one after the other. So something happens, and then after that, something else happens. These are successive events. They happen in succession. One thing happens, and then after it, another thing happens. In order for us to have a success, both things have to happen. The first thing and the second thing. And the way that we're going to find the probability of the whole thing then, of the first thing happening and the second thing happening, is we are going to find the individual probability of each event and then multiply those probabilities together. This should feel very reminiscent to the fundamental principle of counting. That was find a number of possibilities for each stage in the problem and multiply those. Now we're finding the probability of each event that has to happen and multiplying those together. Let's look at an example. A jar contains 5 green, 3 white, and 4 red marbles. A marble is selected, then replaced, and then another marble is selected. So those are our successive events. One thing happens, then another thing happens. First, I take out a marble, then it's replaced, meaning I put it back in the jar, mix them up again, and then another marble is selected. So I pick one, write down what it is, put it back in, mix them up, pick out another one. And our question here is this: what is the probability that the first marble is green and the second marble is red? So I have successive events, one after another. So what I'm after here, what is the probability that the first marble is green and the second marble is red? So I need the probability of green followed by red. The way that we're going to answer this question is we're going to find the probability that the first marble is green. We are going to find the probability that the second marble is red, and we're going to multiply those together. So, probability the first marble is green. Remember, most important thing about probability is successes over outcomes. So let's see here. Total number of outcomes I have in my jar is, let's see, 5 and 3 is 8 and 4, that's 12. So the probability I get a green on the first one is 5 out of 12. Let me know if you see any numbers that don't make sense. All right, so I reach in this jar and I pull out a green one. Then I'm going to put it back in, mix them all up, and now I'm going to try to get a red one because I need the second one to be red. Well, I put my original marble back in, so there's 12 outcomes, and there are 4 reds in the jar, so the probability of getting a red on this pick is 4 out of 12. All right, well, probability of getting green on the first draw was 5 out of 12. Probability of getting red on the second draw was 4 out of 12. So the probability of getting green followed by red is what I get when I multiply those together. 5 times 4 will be 20. 12 times 12 is 144. So the probability of getting green followed by red is 20 out of 144. We are going to do problems that are significantly more complicated than this one later on, but for right now, this is compound probability. This is one event followed by another event. We find the probability of each thing, multiply those together, and that is the probability of getting green followed by red. Are there any questions about anything we did to come up with that result? All right. You're probably pretty comfortable with this idea at this point, that we could write probabilities as fractions or as decimals. If we were asked to write this one as a decimal rounded to the nearest hundredth, we just have one more step to do, and that's divide 20 divided by 144. And if we do that, 20 divided by 144, we get 0.1388888. That continues. And if I was supposed to round to the nearest hundredth, I'd look one space to the right. That's 5 or bigger, so we would round this up and have 0.14. So as a fraction, this would be 20 over 144. You could reduce that if you wanted to, but you don't have to. As a decimal, rounded to the nearest hundredth, it would be 0.14. Please let me know if you have any questions on that before we move on to another one. All right. What I find is you all tend to do extremely well with most things, so I feel like I can move along at a pretty good pace. But you let me know if that's not true. I'm going to have you try this one. A jar contains 5 green, 3 white, 4 red marbles. A marble is selected and replaced, then another marble is selected. What's the probability the first marble is red and the second marble is white? I'll set up a poll for this one and let you try it. So we've got this jar with marbles in it, and we pick a marble out, put it back in the jar, pick another marble out. What's the probability we get red followed by white? And this is a straightforward successive events question. Like I said, we're gonna get more difficult as the day goes on, but for right now, this is just straightforward. Find the probability of each event, multiply those together. That's what successive events, that's how we find the probabilities of successive events. We'll go another 30 seconds on this and then talk about it. Okay, not quite unanimous, so we'll be patient and careful as we go through this. Let me know if you have questions or if we don't clear it up. So what we're after here is the probability of red followed by white. And as we saw before, there are 12 total marbles in this jar. So the probability of getting red on the first draw is 4 out of 12. Then we put that marble back in the jar, and the probability of getting white on the second draw is 3 out of 12. Similar to the fundamental principle of counting, we're going to find the probability of each event and then multiply those together. And when we multiply, 4 times 3 is 12. 12 times 12 is 144. So the probability of getting red followed by white is 12 out of 144. We could reduce that, but we don't have to. We could convert it to a decimal, but we weren't asked to. So 12 out of 144 will be just fine here. Any questions on that before I look at one that's very similar to this with one major important change? Okay. A jar contains 5 green, 3 white, and 4 red marbles. One marble selected, then another marble is selected without replacement. So this is the new thing here. What that means is when I pick that first marble out, I do not put it back in before I pick the second one. That's going to change things for us. And what we're asked for here is the probability that the first marble is red and the second marble is white. So we need red followed by white. That's the same thing we had last time. Probability will be a little bit different here though, because this time it's being done without replacement. All right, well, just like it was before, we have 12 total marbles in this jar, and I need red on the first draw, and the probability is 4 out of 12. All right, here's where this without replacement comes in. So I reach in and I pull it out, and I got a red one. I am not going to put that red one back in. So now instead of having 12 total marbles in the jar, now I only have 11. The probability of getting white on this second draw, well, there's still 3 white marbles in the jar, but there's only 11 total now. So the probability of getting a white one there is 3 out of 11. So the probability of getting red on the first draw was 4 out of 12. Probability of getting white on the second draw was 3 out of 11. So the probability of red followed by white is what we get when we multiply those together. 4 times 3 is 12. 12 times 11 is 132. So the probability of getting red followed by white this way is 12 out of 132. Last time it was 12 out of 144. Basically what changed is by doing this without replacement, the number of outcomes in the second draw was smaller, so the total number of outcomes overall was smaller. And that's what changed from the last one to this one. Any questions about what we did there and what without replacement means for us? Okay, we're going to look at one that reads more complicated than it really is. Catherine has applied for a job with Globo Corp. There's a 48% chance she will get an interview. If she gets an interview, there's a 30% chance she will get the job. What's the probability she will get the job? And this one we're going to write as a decimal rounded to the nearest hundred. So your first thought might be, how is this successive events? And that's a reasonable question, but basically there's a process here, right? First, she's going to have to get the interview, and then she's going to have to get the job. So those are our successive events. First, the interview, then the job. So those are our successive events, one thing, then another. So, all right, what I need to do is find the probability of getting an interview, probability of getting the job, and multiply those together. Well, in this particular setup, I'm not given like successes and outcomes. Instead, I've just been told there's a 48% chance. Well, 48% is a percent, but we could write that as a decimal, as 0.48. And what that is, this is the decimal version of the probability that she's going to get an interview. So we need the probability she's going to get an interview, and right there it is in the problem for us. And then similarly, if she does get an interview, so the first thing happens, now we're looking for the second thing, there's a 30% chance she gets the job. Again, we're not given successes and outcomes, but we could rewrite that 30% as a decimal. And this is the decimal representation of the probability that she gets the job after the interview. And so really all we've got here is the probability of getting the interview and then getting the job is, well, there's a 48% is the probability she gets an interview. 30% is the probability she gets a job afterwards. And we multiply those together. And so we just need to multiply 0.48 times 0.3, and we get 0.144. We were told here that we're supposed to round this to the nearest hundredth. So we'll find the hundredths place, look one space to the right. That's 4 lower, so round this down to 0.14. When you read this, it can feel a little overwhelming because, well, I don't know what my successes are. I don't know what my outcomes are. Well, take a deep breath and realize you've been given the probability of getting the interview, you've been given the probability of getting the job, and you just need to multiply those together. That's all. Okay, now we get to the part of section 4.4 that is more involved. So far, we've just looked at find the probability of each event, multiply those together. And that's still going to be true and still going to be relevant for us. But we're going to get into problems where we're not asked for red followed by white, or green followed by red, or get the interview, get the job. We're going to be asked for different types of questions where we're going to have to be a little more expansive in what we find. When the situation is more complicated, that's when we need a tree diagram. That's what we're going to talk about next. Tree diagrams are great when our problems are a little more complex. And to say that another way is if we're not looking for a single specific outcome. When I say single specific outcome, what I mean is like red followed by green, red followed by white, white followed by green, interview followed by job. Those are very specific. It's just a single specific outcome. What we're going to see shortly are some problems that aren't necessarily looking for something like that. And in order to keep track of all of our outcomes and all the probabilities that go with them, what we're going to do is we're going to create tree diagrams. We're going to start with an extremely simple situation, extremely simple tree diagram, just to sort of get our feet on the ground. Here's an example. Parents are going to have 2 children. Create the tree diagram for this situation. So we start from just nothingness, and they're going to have that first child, and it's either going to be a boy or a girl. We're actually going to put the probabilities right here on our tree diagram. And roughly, I think it's a little bit higher than 50% that you have a girl, but we're going to ballpark this to the probability of having a boy is 1/2, the probability of having a girl is 1/2. So there's the first child. Now, they're also going to have a second child, and the first one's a boy. That means we're up here, and so the second child could either be a boy or a girl. And the probabilities that goes with those are 1/2 and 1/2. Really important thing about reading and making tree diagrams that I want you to see right now is this second child that's up there, that is if the first one was a boy. We also have to consider what if the first one was a girl? And so we need to build a second child into our tree diagram where the second one was a girl. And so if the first one was a girl, the first one's a girl, we're down here, and then the second child could either be a boy or a girl. And the probabilities that go with that, well, are 1/2 and 1/2. I'm going to pause for a minute because, and like I said earlier, it feels like you guys, for the most part, are doing extremely well with the content, and I don't want to overstate something, but just to make sure here, our first child is right there in that column. It's either a boy or a girl. And then after that, sometimes students will read this and say, well, there's 1, 2, 3 children. I thought they were only having two. How come there's three? It's a reasonable thing until you've kind of got some experience with tree diagrams to think, here's the first child, and then this column over here, this is the second child. And what's going on is up here is the second child if the first child's a boy. Down here is the second child if the first child is a girl. And so what we're doing here is we're accounting for every possibility. Here's the first child, and then here is the second child. So this is what our tree diagram looks like for parents having two children. We've made our tree diagram. Do you have any questions about what we've got here, how we built this thing, and what it shows us? Okay, you tell me if you change your mind. Now, what are we going to use this for? Because, you know, after all, we want this thing to have a purpose. Here's what we're going to use it for. We're going to use this tree diagram to create our sample space, everything that could possibly happen, and the probabilities that go with each outcome. Here's how we do that. One of the things that can happen with this family is they could have a boy followed by a boy. If they follow that path, boy followed by boy, then they end up here with boy followed by a boy. And the probability of ending up with two boys is what we get when we multiply the probabilities along that path. These are successive events. We had a boy, now we're having another child, it's a boy. We multiply those probabilities together just like we've done up to now. 1/2 times 1/2 gives us a probability of 1/4. We're going to do this with every path on the tree diagram. We could have boy followed by girl. If we follow that path, then we have boy followed by girl. The probability of boy followed by girl is what we get when we multiply the probabilities along that path. 1/2 times 1/2 is 1/4. Please let me know if you see anything that doesn't make sense or is confusing or you're not sure of. We could have girl followed by boy. Girl followed by boy. We multiply the probabilities along that path. 1/2 times 1/2 is 1/4. And then finally, we could have girl followed by girl. Girl followed by girl. Multiply the probabilities along that path. 1/2 times 1/2. That probability is 1/4. When I said earlier that this is a very simple, basic tree diagram, it's not a very interesting tree diagram. All the probabilities are the same. When we get to our sample space, all the probabilities in our sample space are the same. But what this tree diagram has allowed us to do is create this sample space. We have everything that could possibly happen. Boy, 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 girl, girl, boy, girl, girl. That's everything that could possibly happen, along with the probabilities that go with those outcomes. Now we've created our sample space. Are there any questions on what we've done to get here? Excellent. All right, let's look at some questions. Parents are going to have two children. Find the following probabilities. The first question we're given is, find the probability that they have two boys. So here what we're looking for is the probability of boy followed by boy. To be honest with you, that is a single specific outcome. We don't really need a tree diagram to answer that question. We could do that one without a tree. Find the probability of a boy, find the probability of a boy, multiply those together. But since we made the tree, we might as well use it. We'll go back and we'll look at this sample space that we made. And what we'll see here is, well, boy followed by boy is right there. It has a probability of 1/4. So to answer that question then, what's the probability of boy followed by boy? It is 1/4. Up next, we get to the real value of the tree diagram. If we're asked for the probability of something like this, that is not a single specific outcome, this says, what's the probability of getting exactly one boy? This doesn't say boy, boy, or girl, girl. This says exactly one boy. There may be more than one way to have this happen. This is not a single specific outcome. For this one, we need our tree. And we're going to go back and we're going to look at our sample space to find where we have exactly one boy. So we'll go back and we'll take a look. So I'm looking for the outcomes that have exactly one boy. Well, this says two boys, so that's no good. Boy followed by girl. Yep, exactly one boy. Girl followed by boy. Exactly one boy. Girl followed by girl, that doesn't have any boys, so that's no good. So it turns out when I look at my sample space, there's more than one way to have a success here. There's more than one way to have exactly one boy. I could have exactly one boy this way or this way. And you might remember the word or when we talked about that last week. When the word or comes up, we have to join these things together. We have to count them both. And so what we have to do here is we have to add these probabilities together. We have to take the probability of getting boy girl and add it to the probability of getting girl boy, and the probability of getting exactly one boy is 2/4. I'm going to go write that answer down. I'm going to come back here and talk about something that may be on your mind. It may not, but it might. So the probability of getting exactly one boy is 2/4. All right, looking back at our tree. Sometimes students will get a little bit confused with, okay, wait a minute. I was multiplying, now I'm adding. How do I know when to do which of those? It's a good question. It's a perfectly reasonable question to think, okay, wait, there's sometimes when you multiply and sometimes when you add, and I can clear it up for you very simply. When we are, after we've made our tree diagram, so we've made our tree, and then we're looking to create this sample space over here. That's when we multiply. When we are moving along the path, one event followed by another, that's when we do our multiplying. After we've created this sample space over here, once this sample space is made with the probabilities on it, we are done multiplying. Multiplying is over. At this point, depending on the question we're asked, if it says at least one boy, there may be more than one way to have a success. If that happens, if there's more than one way to have a success, we can have a success this way or this way. That's when we need to add probabilities together. So the multiplying happens, we've built our tree, we're making our sample space. After we've got the sample space and those probabilities, multiplying's over. Now, depending on what the question is, if there's more than one way to have a success, that's when we need to add. There's one more question on the next page, and it said, what's the probability of having at least one boy? So exactly and at least are different from each other. We've seen that before. Exactly one boy, at least one boy. So at least one boy means one or more. So what we're going to consider successes here is one or more boys. So we'll go back and we'll look at our sample space. And we look at this first up here. Do I have at least one boy? Yeah, I have two. At least one. One or more, we're good. At least one boy. Yep. At least one boy. Yeah, I got one there. At least one boy. No, that one's no good. So the probability of getting at least one boy, well, that can happen this way or this way or this way. So I need to add all three of those together. And then 1/4 plus 1/4 plus 1/4 is 3/4. So the probability of getting at least one boy is 3/4. I will admit, the probabilities involved in that particular tree diagram are not the most interesting or challenging. We're gonna change that shortly. But I wanted to work with something very simple to start with, just to get the ideas across. Are there any questions about what we did to answer any of these three questions, or anything about what's going on with this tree diagram here? Excellent. Okay. Let's make it a little more difficult. I may ask you a question or two as we build this tree diagram. But let's establish our situation here first. A jar contains 6 blue and 2 yellow marbles. 2 marbles will be drawn, one after the other, without replacement. That's really important. Create the tree diagram for this situation. So we're going to make a tree diagram here. I'm going to walk up and I'm going to draw a marble out, and it's either going to be blue or yellow. I need the probabilities of those. And this is where I said the probabilities are going to get more interesting, because you'll see in short how they do. So let's see, I have 6 blue and 2 yellow, so I have 8 total marbles in the jar. So the probability of me getting a blue one is 6 out of 8. The probability that I get a yellow one is 2 out of 8. Let me know if anything so far is confusing, doesn't make sense, not sure where that number came from. Okay. After I pick the first one, I'm going to pick a second one. If I'm up here, that means the first one I picked was blue. The second one is either going to be blue or yellow. And now is where I'm going to ask you to tell me something. And if you're uncomfortable or you're not sure, you can tell me that too. But what I want to know then, I've picked a blue one. This is being done without replacement, so I have left it out. What's the probability of getting another blue one? What probability goes on that path? I don't think this is necessarily easy. If you get this, then the rest of this tree diagram is going to be great for you. So that's my question. All right. Couple of 5s in there, Kevin, Jessica, that's excellent. So I started out with 8 marbles in my jar, 6 of them were blue. And I picked out a blue one, and since this is being done without replacement, when I pick that blue one, I leave it out. So after I pick that blue one and I leave it out, I have 7 marbles left in the jar. I started with 6 blue, I picked out a blue, so now I only have 5 blue left. So you were both right about the 5. The 7 is how many total marbles are left in the jar. Now I have another question for you. There were 8 in the beginning. I picked out a blue one and I left it out. What's the probability I get a yellow one on that second draw? And this is a beautiful reminder of probability of successes over outcomes. I started with 8 marbles. I picked out a blue one and I left it out. So I only have 7 marbles left in the jar. I started with 2 yellows. I picked out a blue one, so both yellows are still in there. So the probability of yellow is 2 out of 7. Excellent, Jessica, very good. Okay, now we need to build the rest of my tree. The first one could be yellow, and I could get a blue, or I could get a yellow. The philosophy down here is the same. It's just what's different is now the first one I picked was yellow. So I picked a yellow one, I left it out, which means I have 7 left in the jar. What's the probability, numerator and denominator, that I'm going to get a blue one after getting a yellow one first? What's the probability that's going to go here? 7's in the denominator for sure. When you type it, type both numerator and denominator. Excellent, Kevin. Very good. Because I started with 6 blue, the one that I took out was a yellow, so I have 6 blues still in the jar. And then using that same philosophy, and just please tell me if this doesn't make sense, but I started with 2 yellows. I picked out a yellow. There's 7 left in the jar. Only one of them is yellow, so the probability of yellow down there is 1 out of 7. Now I've built my tree. I'm ready to go create my sample space by multiplying successive event probabilities together. So as we do that, we could get blue followed by blue, blue followed by blue, and I need to multiply the probabilities along that path. And now you can already see how this is definitely more interesting than the one we did before. I'll multiply those probabilities. 6 times 5 in the numerator is 30. 8 times 7 in the denominator. Let's see, 8 times 7, 56. So the probability of getting blue followed by blue is 30 out of 56. We're going to do this same thing with every other path in the diagram. We could get blue followed by yellow, which would be these two probabilities multiplied together. 6/8 times 2/7. In the numerator, 6 times 2 is 12. In the denominator, 8 times 7 is 56. One thing that's really nice is our denominator is always going to be 8 times 7, so we're always going to have 56. I could have yellow followed by blue, yellow followed by blue. I'm going to multiply these probabilities together. 2/8 times 6/7. 2 times 6 is 12. 8 times 7 is 56. And then just one more to go. Yellow followed by yellow. 2/8 times 1/7. We'll multiply the probabilities, and 2 times 1 is 2. 8 times 7 is 56. And now we made the tree diagram. We've created our sample space. We're done multiplying. Multiplying is over. When I go answer questions about this, I may have to do some adding, but the multiplying is over. Let's go see what some questions look like. A jar contains 6 blue and 2 yellow marbles. 2 marbles drawn, one after the other without replacement. That's what we just drew the tree diagram for. First question says, what's the probability that they're both yellow? To be fair, this is yellow followed by yellow. We wouldn't really need a tree diagram for this question. We could just find the probability of yellow on the first, yellow on the second, and multiply. But since we've gone through all the trouble of making the tree, we'll go back and look at it, and we're trying to identify both yellow. That's right here. That's the only one that has both yellow. So 2 out of 56 is the probability of getting yellow followed by yellow. Please let me know if you have questions. Okay, the second question, a little more involved, says what's the probability of at least one blue? Okay, this is where I need a tree diagram because this is not a single specific outcome. This isn't yellow, yellow, or blue, yellow, or yellow, blue, or blue, blue. This is at least one blue. There could be more than one way to have a success here. What's the probability of at least one blue? So I go back and I look at my sample space and I see at least one blue. Well, I have at least one blue here. I have at least one blue here. I have at least one blue here. So I could get at least one blue this way, or this way, or this way. Since there's more than one way to have at least one blue, I need to add those probabilities together. And when I do that, let's see what I have here. I have 30 over 56 plus 12 over 56 plus 12 over 56. When I add fractions, the denominator stays the same. I add the numerators. Let's see. 30 plus 12 is 54. And so the probability of getting at least one blue is 54 out of 56. If we just think about this for a minute, I mean, imagine that we have this jar with 6 blue and 2 yellow, and you're going to pick one out and leave it out and pick another one out. The chances you get at least one blue are pretty high. And that's what this probability shows us. You know, probability of getting at least one blue is 54 out of 56. Almost a certainty. So the probability of at least one blue was 54 out of 56. And then here's one we haven't seen yet. The probability that the second marble is yellow. Oh, okay. Well, let's go figure out how to find that. Second marble is yellow. So blue, blue. Nope. The second one was blue, so that's no good. Blue followed by yellow. Yes, the second one was yellow. Yellow followed by blue. There's a yellow one in there, but the second one was blue, so that's no good. Yellow followed by yellow. Yes, the second one is yellow. So I could have the second one yellow this way or this way. So I need to add those two probabilities together. 12 out of 56 plus 2 out of 56. Probability that the second one is yellow is 14 out of 56. Okay. How are we doing? I'll tell you that tree diagrams are for some students, this is one of the most challenging lessons of the whole semester. The tree diagrams with the marbles in the jar. My sense is we're doing pretty well, but I guess my best way of finding that out is to let you try one of these start to finish. So I'm going to have you try one where you draw the tree, put the probabilities on there, multiply to find the sample space, and then use that sample space to answer some questions. So that's what we're going to do next. Here goes. An ice chest contains 9 cans of ginger ale and 5 cans of orange soda. 2 cans will be drawn, one after the other, without replacement. What is the probability of getting exactly 1 orange soda? So from the practical standpoint here, you can think about this as, you know, you're out at the park, you're having fun, and 2 of your friends say, "Hey, go over there and get us a pop out of there." And and one of them wants ginger ale and one of them wants orange. And for whatever reason, you're going to have to do this blindfolded. You're doing it at random. You're going to pick one, then you're going to pick another one, and you want exactly 1 orange so that you get what your 2 friends wanted. We're looking for the probability of that actually happening. So make a tree diagram for this with ginger ale and orange soda being your potential outcomes. Put the probabilities on there. Then you're going to draw a second one with ginger ale and orange as your potential outcomes. Put the probabilities on there. In order to build that sample space, we're going to multiply the probabilities together along each path. And then once you have your sample space made, that's when you can answer the question of what's the probability of getting exactly 1 orange soda. I'm going to let you do this start to finish with the exactly 1 orange soda question in the poll. And then we'll draw the diagram together, and then we'll find the answer together. But I want to let you just try this one all the way from start to finish on your own and see how it goes. My sense is that you're doing really well. This is my chance to find out. So I'll make a poll for this one, and I'll give you plenty of time. We don't have to be in a hurry. We've got a few more things we're going to do with this ginger ale and orange setup, but I want to give you plenty of time to work on this one. And I will say, for some students, these are the most challenging questions we see all semester. Maybe some of the trigonometry back from chapter 1, but these are up there with the most challenging questions we work on. I will say, the question you're doing right now is as challenging as section 4.4 will get. If you can do this one, then you're in really good place with section 4.4. Section 4.5 on Thursday has some challenging concepts in it, but honestly, I think this is probably the top of the mountain for the week. That's not to scare you off, it's the opposite. My sense is that you're doing really well with this, and we'll kind of see how this poll turns out. And if it goes as well as I hope, then both you and I can feel really good about where you are with the tree diagram idea. And I guess I should also say, if this doesn't go that well, that's okay. We've got plenty of time to practice before we get to a place where we're doing homework, where we're doing quiz, and then eventually exam questions like this one. All right, this is one of those where I want to give you enough time to do it, but I don't want to give you so much time that you've kind of hit a wall. I think what I may do is cancel the poll on this one, and we'll do it together, and then we'll just talk about how it turned out. So let's take a look at this one together. You let me know if you see something that doesn't make sense. We're going to start out by drawing our tree diagram. When we do that, we're going to have ginger ale or orange for the first can that we pull out of the ice chest. Altogether, there are 14 cans. So the probability of getting ginger ale is 9 out of 14. The probability of getting orange is 5 out of 14. Again, if you see something that you're not sure of where it came from, please let me know. Then we're going to take a second can out that's either going to be ginger ale or orange. Now, if we're up here, that means the first one we picked was ginger ale. And so now we have 13 left in the ice chest, and we had 9 ginger ale to start with. We picked a ginger ale, so there's 8 left. We had 5 orange when we started. We picked out a ginger ale, so we still have 5 orange left out of the 13 that are in the ice chest. Right? The first one could be orange, and then the second one's either going to be ginger ale or orange. And this is going to change our probabilities a little. We've got 13 left in the ice chest. And of those 13, let's see, I started with 9 ginger ale. I took out an orange, so I still have 9 ginger ale in there. 13 left in the ice chest. I started with 5 orange. I took out an orange, so I have 4 left. Okay, I've got my tree diagram built, and I have all my probabilities put on my tree. Now I need to find my sample space. I could have ginger ale followed by ginger ale, which is what I get when I multiply these two together. 9 times 8 is 72, but I don't know what 14 times 13 is. So 14 times 13 is 182. So keep in mind what we just found there. The probability of getting ginger ale followed by ginger ale is 72 out of 182. Now we're going to do the same thing with the others. Ginger ale followed by orange is 9/14 times 5/13. So 9 times 5, that'll be 45 out of 182. Orange followed by ginger ale, 5/14 times 9/13. 5 times 9, that'll be 45 out of 182. Down at the bottom, orange followed by orange, 5/14 times 4/13. 5 times 4 will be 20 out of 182. And so now we've built our sample space. We're done multiplying. Now we're ready to start answering questions. If anything in drawing the tree, putting the probabilities on, or finding the sample space didn't make sense, please tell me. Now we're ready to answer this question over here. What's the probability of getting exactly 1 orange soda? Ginger ale. Didn't get any orange soda. Ginger ale, orange. Hey, that's exactly 1 orange. Orange, ginger ale. That's exactly 1 orange. Orange. Nope. That's 2 oranges. That's not exactly 1. So I could get exactly 1 orange this way or this way. So I need to add those probabilities together. And 45 out of 182 plus 45 out of 182 will be 90 out of 182. With this sample space in mind, I want you to try a couple more questions. So now we've got our tree done, we've got our sample space done. Now it's just a matter of answering questions. Same setup, an ice chest with 9 ginger ale, 5 orange, 2 cans drawn, one after the other without replacement. Our question this time is, what's the probability of getting at least 1 ginger ale? And instead of a poll for this, I'll just have you type it for me. What's the probability of getting at least 1 ginger ale? And we can go back and look at it. Probability of at least 1 ginger ale. Keep in mind that at least 1 means 1 or more. So the probability of at least 1 ginger ale. And once you have it, you can just type it in for me. And we'll see how we're doing with this one. The difference between at least and exactly is going to be really important in this section. Identifying, drawing the tree, putting the probabilities on, finding a sample space. All those things are important. And so is identifying the outcomes that are successes for a given situation. And so here we want the probability of at least 1 ginger ale. All right, 162 out of 182. Let's see. At least 1 ginger ale. So yes, I have a ginger ale here. Yes, I have a ginger ale here. And yes, I have a ginger ale here. Down here, I don't. So I could get at least 1 ginger ale this way or this way. or this way. So I need to add those probabilities together. And let's see, 45 and 45 is 90 plus 72. Sure enough, 162 out of 182. That's the probability of getting at least one ginger ale. Let's try one more related to this situation. Same setup, ice chest with 9 ginger ale, 5 orange, 2 cans drawn, one after the other without replacement. This time, what's the probability the second can is orange? So, probability that the second is orange. And again, you can just type that in and we'll take a look and see what is the probability that the second one is orange. And I have said several times today that these can be challenging. I also want to point out that I definitely think you can do them. And we're having good luck with what we're getting here for answers. All right, got 65 out of 182. Let's take a look. Second one's orange. Well, second one's ginger ale. That's no good. Second one's orange. Yep. Second one's ginger ale. That's no good. Second one's orange. Yep. So we need to add these two together. Sure enough, 65 out of 182. Outstanding. Does anybody have questions on the 3 questions we worked on related to this scenario? Exactly 1 orange, at least 1 ginger ale. The second one is orange. All right, very good. This is not something that's going to be a focus for us, but I just want you to see what it looks like if we had 3 events in a tree diagram. And the key here is to leave space for yourself. A coin is flipped 3 times. Create a tree diagram for this scenario. So the first time the coin would be flipped, we would either get heads or tails. Those probabilities would be 1/2. The second time the coin is flipped, we could get heads or tails. And all those probabilities would be 1/2. And so this is what we've looked at so far, where we have 2 events, right? Here's our first coin flip is either heads or tails. And here's our second coin flip, because at the top of our tree, this is if the first flip were heads. At the bottom of our tree, this is if the first flip were tails. If we wanted to have a third flip, then our tree diagram has to keep going. And we would have heads or tails off of here, heads or tails off of here, heads or tails off of here, heads or tails off of here. And again, all of those probabilities would be 1/2. And so essentially what we've got here then is we've got our first flip, our second flip, depending on the first one, and then our third one, our third flip, depending on the first 2 flips. And that's what a 3-event tree diagram would look like. They can get a little clumsy, they can get a little messy. That's why it's not going to be a focal point for us, but I do want you to kind of at least see what it looks like. We would do the same thing here. We would make our sample space. We would have heads, heads, heads. And the probability would be 1/2 times 1/2 times 1/2, or 1/8. We could have heads, heads, tails, heads, heads, or excuse me, heads, tails, heads, heads, tails, tails. I'm going to go ahead and put them on. Why not? Sorry about this. I got a little sloppy there. So that probability was 1/8. We could have heads, heads, tails. Probability is 1/8. Heads, tails, heads. Probability is 1/8. Heads, tails, tails. Probability is 1/8. And then there are going to be 4 more outcomes. tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So it's a way to build a sample space. For one like this, really, I would think this is 3 heads, 2 heads, 1 heads that way, and so we could build this sample space. I just want you to see what a diagram would look like if it had 3. If it had 4, it becomes a very hard thing to even draw without a giant sheet of paper and leaving yourself lots of space. Okay, couple of notes about homework before we wrap up for today. Some questions in this homework may be related to basic probability. We definitely have instances where we're looking at just basic probability, which, remember, probability is successes over outcomes. We see that when we make a tree diagram. With the probabilities along the way, we're using successes over outcomes. If you're working on problems in the book, there's some successes over outcomes in there just to sort of refresh your memory and review the idea that probability is successes over outcomes. A lot of the questions you'll see are what we did at the beginning of class today, where we're after a single specific outcome, red followed by white, interview followed by job. When those are the case, you don't have to make a tree diagram for them. Instead, you can just find the probability of each event and multiply them together. And then finally, what we saw at the end of class today, some will involve making and using a tree diagram. Just be careful when you make your tree. Make sure you put the probabilities on there and be very careful that you answer the question that's being asked. And what I mean by that is make sure you're identifying successes that are related to the question you've been given. Whether it's the second one is a certain color or the at least and exactly, make sure you're actually finding the